Hi class, welcome to exercise 7F, applications of parabolas. And in today's lesson, you'll be doing example 13, which is applying quadratics in problems. And your pre-learning for this will be questions 1 and 5 in the new book and questions 5 and 7 in the old book. And that's all the examples for today's lesson. So we'll see you in the introduction. We've already seen applications of quadratics in this unit. However, using parabolas, which are the graphs of quadratics, we're able to get a lot more information. One thing we could do is model physical objects, such as this bridge. Let's pop over to GeoGebra to see how I've done that using this applet. Now you can see everything in this picture is a straight line, except for this red support span, which I've modeled with a parabola. In doing so, I was able to make these green lines fit with perfect length, and by changing the slider, I could have a lot more of them. And the way I've done that is I've made the height of each line fit exactly to the parabola, and the base is the same height as the road. However, the best thing about using parabolas rather than quadratic equations is that we can answer a lot more questions. And this is because when using quadratics, we figured out the dimensions of shapes when we already knew what was the area of that shape. So the type of problems we worked on previously was, for example, if a rectangle has a perimeter 40 meters and an area of 64 meters squares, what are its dimensions? Well, seeing that the perimeter is 2 times the width and 2 times the length, and that was 40, which we can write as 2w plus 2l equals 40. And of course, area is width by length, which we've got is equal to 64. And then if I just focus on the equation for perimeter, dividing both sides by 2 means that width plus length has to equal 20. So when I rearrange that equation, I can represent width as 20 minus the length. And then when I sub it into width times length, we've got width as 20 minus L. So we end up with 20 minus L times L is equal to 64. Okay, that's really just saying width times length. So now I can find what's the value of L by creating and then solving a quadratic. So let's begin by expanding the left-hand side, and we'll end up with 20 times L minus L squared equals 64. And now I want to move all the terms to one side, so we have a quadratic that's equal to 0. And I can factor that easily as 0 is equal to L minus 4 times L minus 16. So we now find that the length of the quadratic could be either 4 or 16. And that was well and good if we were totally focused on an area of 64. But what if we're interested in more than one size of area? Well, if we just use quadratics, they're going to miss a lot on their own. And what is great about a parabola is they let us see all the possible areas. And they will also tell us what the maximum and minimum area is when we consider the turning point. So for example, if we've got a rectangle with a perimeter of 40, then it's going to have a width and length just like this. And because two sides of this rectangle are the width and two sides are the length, we could describe the perimeter as 2w plus 2l equals 40. Okay, we've already covered that with our talk on quadratics. And of course that means that width plus length equals 20. Okay, that's just simply dividing both sides by 2 and rearranging it, I can represent width as 20 minus length. And because the area is width times length, and because we've described width as 20 minus L, we can rewrite that as 20 minus L times L, and then expand it to express it as 20L minus L squared. So at this stage, obviously we're not looking that different to the quadratics, but let's keep going and see what the differences will be. So it really doesn't matter what term we use, so we could call L x when we look at all the possible areas. And the reason I'm doing that is just to keep things familiar. So then we could look at the equation y equals 20x minus x squared as a way of explaining the area from here. And we could graph it on these axes where y is going to be our area and x will be our length. And looking at that equation, you can see that y is going to equal 0 when x is 0 and x is 20. Okay, and that's because 20 times 20 minus 20 squared is obviously 0, and 0 times 20 minus 0 squared is also 0. Now the axis of symmetry is going to always be in the middle of those two x-intercepts. So the middle of 0 and 20 is 10. And we'll end up with a parabola that looks just like this. Wow, still bad at them, aren't I? And of course the turning point will be on the x-axis, so I want to redraw it to make sure it does actually look like that. That's probably as close as I'm going to get, so let's put in the turning point. Okay, so we know that the x value there is 10. Now as y represents the area, we could see that it's a maximum there, right? And as I've already marked in, the x value there is 10. So when x is 10, y is going to equal 20 times 10 minus 10 squared, which is 200 minus 100, which is 100. So let's mark that in as well. So we can see we've marked in the maximum has a length of 10. So that means that the width is equal to 20 minus the length, which is also 10. So we know now that the maximum area possible for a rectangle with a perimeter of 40 is a square with side lengths 10 and has an area of 100, just as we marked in. And we could find the dimensions for any area that we wanted to choose from this point on, just using this parabola. Now, isn't that a lot more interesting than finding what the dimensions are just for one particular area? All right, we'll see you in the next section. As discussed in the introduction, just using quadratics alone will only solve a specific problem. However, graphing the quadratic with a parabola allows you to see all of the possible solutions. So not only do we see the dimensions for all possible values in an area, for example, we could see general solutions such as the maximum and minimum by using the turning point. However, you really do need to take note that it's important to think about what are sensible values. So for example, when we're working with lengths and areas, you need to know that lengths and areas can't be negative. Okay, so let's put all this into action with example 13, where we have a piece of wire that's 100 centimeters and it's bent into a rectangle, such as this one. And note down the perimeter is equal to 100. And let's denote the width as x. So in part A, we're asked to express the length now in terms of x. Now, because the perimeter of a rectangle is 2 times the width and 2 times the length, P is going to equal 2 times W plus 2 times L. And subbing in 100 for perimeter and x for W, we've now got 100 equals 2x plus 2L. And of course, we can divide both sides by 2, so we end up with 50 is equal to x plus L. And rearranging that, we now get L is equal to 50 minus x. Okay, so we've now expressed L in terms of x, and of course width is x. So part B, where we need to write an expression to express the area of the rectangle in terms of x, and with those dimensions marked in on the side, it should be a little bit clearer. So the area has to be width times length, so that means that area is equal to x times 50 minus x. And we've got our area now expressed in terms of x. Okay, let's move on to part C, where they ask us to decide on what would sensible values of x be. And of course, x being the width must be greater than 0, and 50 minus x being the length must be greater than 0 as well. And that's simply because lengths have to be positive, right? So therefore we've got x greater than 0, and moving the x the other side of the inequality, we've got 50 is greater than x. And it will look neater if we flip it around and say 0 is less than x and x is less than 50, because I like to write it in one line where I'd say 0 is less than x, which is less than 50. Okay, so our range is somewhere between 0 and 50. All right, in part D, we need to sketch the area compared to width. So if we let area be y, then we already know that area is equal to x times 50 minus x, so that means that y is equal to x times 50 minus x. And we're going to graph that on these axes here. And I've chosen these ones because I'm only interested in positive values of x and y, okay? So looking at the quadratic equation we've used to describe y, if y is equal to 0, then x is going to be equal to 0, or 50 minus x is going to be equal to 0, which means x will equal 50 there. So let me mark those in on that graph. And our axis of symmetry is always in the middle of the x-intercepts. And the middle of 0 and 50, of course, means x equals 25. So let's mark that in on the graph. And because the turning point has an x value of x equals 25, okay, because we know that the turning point will be on the axis of symmetry, therefore, the y value will be where y is equal to 25 times 50 minus 25. Okay, and that's just by subbing in 25 for x. And that's equal to 25 squared, which is 625. And before I mark that in on the graph, I'm going to try and draw the parabola first. Oh, I think that's actually better than usual, don't you? All right, so we know this turning point is a maximum, and it has x value 25 and y value 625. Of course, I haven't drawn this to scale, okay? It would actually be a lot higher, a lot pointier. As you can see, 50 and 625 are much bigger differences than that. All right, so we've drawn the graph and we've got all the points marked in there. Part E is asking us to determine the maximum area that can be found. Now, because the turning point is a maximum, therefore the maximum area must be 625 because that's the area at this point. So there you go, that's really straightforward in lots of ways, and that's because we get so much information out of a parabola. And finally, in part F, we have to state what the dimensions of the rectangle are with the maximum amount of area. And clearly, when x is equal to 25, we have the maximum area. And seeing x represents the width, therefore the width is 25, and the length is equal to 50 minus the width, which is 25 also. So we've got width and length at both 25. I would love to have a look at this application in GeoGebra, and we can do so with this applet. Okay, let's start here with a width of 5, and we need a length of 45 to get a total perimeter of 100. And you can see this rectangle here, which represents our perimeter of 100. And when we have a width of 5, you can see that the area of the rectangle is 225, and the point on this parabola right next to it is directly above 5 on the x-axis, but it also has a height of 225. Now, changing the width, of course, changes the length. And if I keep on moving that width to 25, you'll see that we'll have an area of 625, which is just like our answer in the question, right? And as the width continues to get bigger, we have less and less area. Hopefully you can see the maximum area for a rectangle of any perimeter is actually the square of the total perimeter divided by 4. And that's something else we can think about later. But another point to notice is that when I've got a width of 45, we've got exactly the same rectangle as having a width of 5. It's just lying on its side. Okay, I think right about now you should pause that video and do question 1 in the new book and questions 5 in the old book. But before you go off and do your pre-learning, I do want to point out that there are lots of questions in this exercise. So perhaps you'd like to try a few more questions than what I recommend for pre-learning. All right, I'll see you in the summary. Okay, so this is the second last lesson of our unit. And I'm hoping that seeing the parabolas in real-world problems helps them seem a lot more real for you. Anyhow, from this lesson, a successful student will be able to set up a quadratic model to solve a worded problem, know how to apply the process of quadratics to identify key features of a graph and relate them to real-life contexts, and finally, be able to identify all the possible values of a variable in a given context. Okay, I hope you enjoyed the opportunity to apply these skills to real-world problems. Hopefully it builds a deeper understanding because our last lesson of this unit is a real doozy. So make sure you're ready to go for that one. All right, See you in that next lesson, either in class or the next video. Bye.